We'll recap some of Morello ISA semantics and verification.
Yes.
Again, a little brief.
All right. So I'm Thomas Bauereiss. I'd like to talk about the formal instruction semantics of Morello, and in particular, the formal verification of a key security property that we did some time ago while Morello was still being developed. And the motivation for that was that when you add Cherry to an architecture like ARM, you have to make sure that you're securely integrated with the base architecture and all the existing features, of which there might be many. And even one flaw in some corner case could compromise the Cherry security guarantees that you're trying to achieve. And if that's a flaw in the hardware that ends up in the hardware, that might be impossible to fix. So with this machine check proof, we, using a formal model of the full instruction semantics, we get confidence that at least this property that we verified actually holds for Morello. Although we did actually catch a couple of bugs while we did the proof, but because we were doing this while the architecture was still being developed, ARM was able to fix these bugs before finalizing the design and manufacturing the hardware. So that's a success. Another useful thing we did with the formal model was to automatically generate a test suite with high specification coverage that was also useful during the development to test the hardware design against the specification and to help with software bring up. So let's look at this formal model. So we used the instruction semantics that ARM themselves wrote in their ASL specification language. And it has all the instructions of Morello, 400 of them, and system level features and address translation and so on. It's around 62,000 lines of ASL, which maybe from a software development perspective, maybe doesn't sound like that much, but from a formal verification perspective, it is a rather big specification. We received weekly snapshots from ARM while the specification was developed, and then we used a tool to automatically translate that into our own specification language SAIL, because then we have access to a number of tools, so we can generate theorem prover definitions. In our case, we used the Isabel prover. Then there is this test generation tool that I mentioned. We can generate an emulator that we can use to run tests or validate the model or use it as a test oracle. And there's also a tool that allowed us to use an SMT solver to check some key correctness properties of, in this case, the helper functions that deal with the compressed capability representation. And using that tool, we did find a couple of bugs early on, even before we started doing the Isabel proof, so that was quite useful. I don't want to spend too much time talking about SAIL, but just to give a brief glimpse at what it looks like. So here you have the decode clause of a PC relative load instruction using capabilities. So it starts with some pattern matching on the opcode, and then it extracts the operands and passes them to the main execute clause of the instruction, which will then do some address arithmetic and perform a memory load, but only after calling this helper function that does a capability check. And here's a helper function in a bit more detail. So it checks that the capability is valid and unsealed and has the right bounds and permissions. And if any of those checks fail, then it will call this AH64 abort function, which will ultimately raise a SAIL exception, which will cause the instruction of this, the execution of the instructions to be stopped at that point. So the memory load will not be performed in that case. And it will also cause, it will also set up a processor exception, which involves writing some system registers and changing the exception level and jumping to the right exception handler. So yeah, and also this code is not overly complex, but there is a lot of detail that we have to take into account when we do the formal verification. So what did we verify? So the property I'm talking about is an architectural property that holds for arbitrary code. And what we are trying to capture is that software cannot escalate its privileges by forging capabilities. So it can only use the capabilities that it is given. And in order to formalize that, we defined a notion of reachable capabilities in a state, which you can think of as an upper bound of the set of capabilities that software is allowed to construct from the capabilities in its state. So this includes the capabilities in registers, capabilities that you can load from memory, via an authorizing capability that is already reachable, and capabilities that you can legally derive from already reachable capabilities by narrowing the bounds, for example, but not widening them. And then this monotonicity theorem says that this is indeed an upper bound. So we are looking here at a sequential model. So if you execute an arbitrary sequence of instructions, the sets of reachable capabilities along the states in that execution does not grow. So software cannot just create new capabilities out of thin air. There are just a few exceptions where non-monotonic transitions are possible. So if a processor exception happens, for example, and control passes to the operating system, then the operating system will have likely a different set of capabilities. So that's a non-monotonic transition. And also, if you use this sealed capability mechanism that Cherry provides that allows you to transfer control to another compartment, for example, that might also be a non-monotonic transition. But the key thing here is that the formal statement of this theorem spells out in detail what these exceptions are and under what conditions they are allowed. And in all other cases, monotonicity is enforced. So to actually prove this, we factored the proof via a narrow abstraction that with just a few intra-instruction properties that capture requirements that we have on any instruction in any Cherry architecture. So if you look at the register and memory effects of instructions, if an instruction accesses a resource, either memory or a privileged register at some point, we require that it has to have a capability in hand. So it must already have access before a capability that authorizes this access. And if it writes a capability to a register or to memory, this capability must have been derived from already available capabilities at that point. And those properties imply this whole ISA monotonicity property, as I said, and they are relatively straightforward to verify for a concrete ISA. Although we still have to do the full proof for the real thing, which did take quite a bit of effort, especially if you also include the preliminary work that we did before on getting tooling into shape so that we can handle specifications of this size in the theorem prover. And then the monotonicity proof itself was done by two people, Thomas Sewell and myself, over the course of a year roughly. And it included some manual work on proving the key helper functions for manipulating capabilities. And then we had to prove that all the instructions and all the helper functions basically use these helper functions correctly. And we created some automation for doing the bulk of that proof. It's not particularly fancy, so it's basically just a tailor-made tool that generates proofs about all the instructions and helper functions in a uniform way with the option to manually tweak when necessary. But it did work well enough, and it allowed us to keep up with these weekly snapshots from ARM that we received. So we then just regenerated the proof, and this mostly worked. So yeah, so I guess for an academic project, this is quite a bit of effort, but we were dealing with an actual industrial scale specification in this case, so it's maybe not too surprising. And we did get out of it this formally verified security properties, and we caught a couple of bugs that are almost unable to fix. So I mentioned already these bugs in the capability compression implementation, and we also found 2 cases of missing capability checks that could have allowed unauthorized memory access or modification of sealed capabilities. And we also found some non-security bugs that we stumbled over during the proof, like some instructions using the ROM memory access type and things like that. And we also found a couple more bugs via testing. So we had this approach to automatically generate a test suite. So we had a tool that a symbolic execution engine for sale that explores the possible execution paths of instructions, and then we use an SMT solver to generate concrete input and output data to construct tests. So this is work that was done by Brian Campbell. And with this, we also found a couple of non-security bugs in the specification, implementations, and also our tooling. And the test suite was also useful for test-driven development of a Q emulator early on, while the architecture before hardware was available. Right, so I talked about formal verification, so I have to have this slide about limitations. So we proved properties of the architecture, so not the actual hardware implementation. So we don't deal with side channel properties. We don't deal with concurrency in this proof. Some parts of the translation pipeline from ASL into the theme prover is not verified. And then, I think as Robert already mentioned, so this property that we proved so far is just a starting point. So you would want to have more properties, not just a general property about arbitrary code, but you want to be able to reason about known code and combinations of known and unknown code. But there is some ongoing work on that Angus is going to talk about next. If you want to know more about this, you can look at the POCL'24 paper for some more details, or you can look at the GitHub repository. And that's what I wanted to say. Thank you.
Questions again?
So you said that it took you 7.5 hours to run the proofs, but I was hoping you would say, and when we found that bug, the proofs were faster to run because you knew that some theorems would not be destroyed or something like that, or?
Yeah, so we found these bugs early on while we were still developing the proof. And so I said we had this tool that auto-generates all the proofs about the instructions and helper functions. And we then loaded this theory, and we could see it would be going through all of those proofs, and at some point it would fail. And Isabel, in interactive mode, it then highlights in red, okay, this part of the proof is failing. You have to look at this instruction or this helper function and figure out what's going on. Either you have to tweak your statement, or you have to look into the details and find that it is an actual bug. And we had some back and forth discussions also with people at ARM about the things we found. Yeah, so we found these bugs, while the proof was being developed, and yeah.
I think my question is, since the proofs are so expensive to run, is there a way to develop a technology where you make little changes and then they're not that expensive to run because some things can be reused? The author wants to say.
I think.
I'll make a comment on changes. For ARM, there are no little changes. So they will go through a design review cycle with multiple authors and all kinds of things before merging an ISA change back into the specification. So they will spend way more than 7 hours coming up with a one-line change. And so the increment, obviously there are good answers probably to this technical question, but in the broadest sort of view, 7 hours is short compared to everything else they're doing. And so it's just not really a big deal.
Yeah, I was going to amplify the second point. 7 hours is nothing compared to the Thomas time. I think you probably could cache some pieces when they make tiny changes, but we didn't.
Yeah.
Did we?
But 7 hours is a lot of time if you have to do it many times until you get the proof right. So
I guess
it's not once 7 hours, it's many times 7 hours.
So I guess part of this proof also includes, processing the specification itself, and that's something we ran once a week basically, and then in Isabel you can save the snapshot of those processed theories, and then you can just load that and don't have to rerun that part of the proof again. Maybe one anecdote that I can tell while I was working on the proof, so I just loaded the theory, and it highlighted a couple of things that went wrong, and I started tackling them from the end, because then it would not invalidate anything that I had done earlier. So I worked from the back to front. Yeah. I don't know if Thomas wanted to say more.
Maybe we should.
Is this on? I was just going to point out that the final proof, it's a combination of the specification that went in, this pre-computation that created it, and some user modification. You can work on the user modification without having to wait 7 hours every time you change something. You see the response to that in seconds or minutes in the worst spot. But If you want to accept a new patch from the start, then you have to wait for a while. So the idea is something like you fudge things locally, you suggest changes. This is similar to software verification. You suggest changes to the developers, and any time that those actually get approved, then you need to at least make coffee, possibly wait overnight for everything to resynchronize, or to check that you really have got everything right. But there's ways to continue making incremental work through your day. But that's...
We should move on very quickly.
Okay, I'm curious about the SMT solver. Was it necessity or it was shortcut? Could you just prove these properties in Isabelle instead of using SMT solver for compression property verification?
Eventually, we also had to prove them in Isabelle, but I guess these are especially critical helper functions in the specification, so it was good to check them early on and iron out already any bugs that we could find cheaply.
Thanks.
Okay, thank you.